Hello, crazy math nerds. I'm back again, the craziest math nerd of them all, Kitty Morgan here. Let's finish this problem, shall we? So we're looking at D, and now they're starting to talk about the second derivative. So I have decided to make like a key for this problem, like you have a key on a map, that kind of helps you understand some things. So let's wrap up kind of the first part and what I wrote. Here's my key right here. There's the key. And notice that in the first part, what was given, G was defined as an accumulator function. So I just took that and wrote it as G. And then in parts B and C, we had to talk about derivative things, because we had the instantaneous rate of change, and they talked about minimum values, or actually absolute, but they talked about minimum values, and you need to talk about critical points and all that. So when we had to talk about the first derivative, well, we know that from the second fundamental theorem of calculus that if you take the derivative of an integral from constant to variable, it's just that function itself. So when you talk about G, then you're talking about the area of F. When you talk about G prime, you're talking about the Y values of F. So let's continue that thinking, that derivative kind of thinking, if you will. And let's see what would happen if we continue the derivatives, because we need to talk about G double prime. So if you take the derivative of G prime, you get G double prime. And if you take the derivative of F, you get F prime. So when we want to talk about G double prime, which we do because in part D it says the second derivative of G, then we're going to have to look at the slopes of F. Okay? So in D, it says that we want to look at these 2 points, at 1 and 2. And it says, of these values, which are coordinates of points of inflection of G. So the first thing we need to do is write down what does that mean for G to have a point of inflection. That means that G double prime would either be 0 or undefined, and that G double prime would change signs. Okay? So they've already told us up here, I'm going to highlight. Well, that's not a highlighter at all, is it? We'll just do this. They told us up here that, oh, that's not good, that G is not defined at 1 and 2. So we already know that those 2 points that we're talking about are not defined, so that's undefined. So let's go back and see how G double prime relates to F. So I'm coming to my key. Here I go to my key. There I am. And I know that G double prime is the slopes of F, or F prime. So I need to see if F prime, this is what I'm thinking, ignore this little box, if F prime changes signs. Okay? So I am going to trace along this function, and I'm looking at this point and this point. And as I trace along the function, I need to see if the slopes change. So here I go. Ready? I really would like a little highlighter, and I can't find one. Oh, there it is. Okay. So here I go. Dun, 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 dun. There's positive slope and negative slope. We have a winner right there. And when I get to 2, notice that I'm decreasing and the slope is negative there. There's not a change. Sorry, 2, you are not a winner of a point of inflection. So 1, 4 is our point of inflection. So we say that at x equals 1, because it says how many x values are x coordinates of the point of inflection. So that's my answer, x equals 1. And that's because G double prime of x equals F prime of x. And F prime of x changes signs at x equals 1. Okay? So let's recap this for just a minute, because this is a kind of a cool thing, because what we've done is we've taken the idea of integration and combined it with all the stuff we did the first semester.